All right, good afternoon and welcome to ECE 164 on current mirrors and biasing. All right, before we get too much into it, since Halloween is right around the corner, I did want to share some of our pumpkins that we've carved both this year and in the past. So this is my wife's very cute kitty cat. This was her much scarier hand. And I think that I win the scariest pumpkin of all. This was my pumpkin in graduate school, showing the very, very scary BJT transistor, along with a Stanford Cardinal S. Um, Hope you all have a great Halloween this year and enjoy. All right, so getting into biasing in analog circuits, it really is that all of the amplifiers that we've designed to date, they require some kind of bias circuit. We've been representing these as simply a current source. Occasionally we'll do voltage biasing for things, um, but we really need to move towards more robust structures as you would commonly see in an integrated circuit. And so what this really looks like is something that's shown kind of down here in the bottom. In particular, this is actually out of one of my papers from when I was at Intel. We'll start off with a voltage reference, okay, and this voltage reference will generate a voltage, ideally that is independent of temperature and independent of process, meaning that if we make, 10 million of these devices, it always has the exact same voltage at the output. Um, then this is connected to a amplifier with a transistor that's in feedback, okay? And what this typically lets you do is that you have an adjustable resistor here where this amplifier is going to force this voltage at this node here to be the same as the positive voltage. And so we're essentially dropping V divided by R current over this resistor. And then we're going to copy that current many times such that we generate programmable current references. Okay? And then we will mirror this around the chip using a structure that we'll talk about in just a second called a current mirror. Okay, and so this is a very, very common structure. We're going to talk about each one of these blocks in today's lecture. All right, so let's start off with an ideal current mirror. So an ideal current mirror is a structure that looks something like this. Okay, what we have is we have a diode connected device. So the gate and the drain of this device M1 are connected together. And then we're taking the gate of M1 and connecting it to another device M2. Okay? Now this kind of structure allows something interesting. It allows for M1 to quote unquote compute the right gate to source voltage. Okay, so if I send I1 into M1, it is going to generate a VGS voltage based on that current. Okay, and so when I connect M2 to that same gate, to the same source, and let's for right now say that they have the same W over L, this means that the current that I'm going to get at the output, I out, is going to be equal to IN. Okay, this is because it has the same VGS and the same W over L. Okay, so to the first order, they have the same input and output current. Okay? Now, why is this so important and why is this commonly used? You can imagine that if the threshold voltage was slightly different on this wafer, okay, VT of these two transistors is still going to match, okay, given their close proximity to each other. And more importantly, M1 computes the bias voltage using this VT. And so when it's mirrored or generated with M2, it correctly accounts for VT. Whereas if I was to send in a voltage here, I would need to precisely know what VT was, as well as all of the other parameters of the MOSFET. Okay. Same thing if mu n Cox was to change. We're using another transistor, in this case, the diode connected M1 device, in order to calculate the right voltage to place on this gate node. Okay. And so if we wanted to look at kind of the ratio of these currents, we could write I out divided by IN, where the they're both equal to 1/2 mu n Cox W over L, VGS minus VT. They have the same of all of these parameters, which means that we're going to get the I out is equal to IN. This also gives us a nice ability, as we'll see in just a second, whereby changing the size of M2, we can ratio the current relative to M1. And so this is a very, very powerful structure that we'll see many, many times in analog integrated circuits. So what are we often trying to do when we're designing these types of circuits? Really, it's about minimizing the error in I out. That is, if I send in 100 microamps and I have the same W over L, I'm trying to get I out equal to 100 microamps. Okay. Additionally, we're going to bias another amplifier or another circuit with this structure. And so we want to minimize what's called the compliance voltage, or the voltage that I need on this node in order to keep this transistor in saturation. Recall that this transistor over here will always be in saturation given its diode connected structure. The transistor on the right, though, will only be in saturation if V out is large enough to allow this device to be in saturation. Okay. Once this device goes into linear, it is no longer a good current mirror. Okay. The output current now heavily depends on the drain voltage, not so much just the gate and source voltage like before. We often also try to minimize the output capacitance. We talked about the frequency response of these circuits. This just comes from a bandwidth perspective, that we want to keep the output capacitance low to keep this node very fast. You also want to maximize the output impedance, R out. So a good current source should have very, very high output impedance. Said another way, that the voltage that is perturbing this node should not modulate the current. And so if I want to keep that property in play, that means that I need a high output voltage or high output impedance. And then lastly, as I was just mentioning on the previous slide, I really want to be able to scale the current. Okay. More often than not, you will see that a current mirror is not used when you want I out equal to I in. It's when we want to scale the current and multiply it by a factor, something like 10 or 20. So let's look at the scaling of this particular structure in a little more detail. All right, so coming back to this circuit, and again, now I'm going to add an extra degree of freedom. Instead of calling them both W over L, I'm now going to label this W1 over L1, this one W2 over L2. And so when I take the ratio of these two currents, I out divided by I in, we're still going to get cancellation of this VGS minus VT term on both sides. We still get mu in Cox canceling for both of these because they're equal, and this 1/2. And so really we're left with this ratio, okay, where using the size of the devices, which I'll call K, we can scale the current by changing the widths and possibly the lengths of these two devices. Okay. And so what I want to do now is look at the scaling geometry in particular and how we might be able to scale this. So it turns out that when we have been looking at our square law model of devices, okay, i.e. our long channel model, if I was to plot the 1 over length on this axis, on the x-axis, and then the drain current on the y-axis, you would see a straight line, okay, and that is simply that as you change the length, you would predict a linear change in the output current. Actual devices have a lot of short channel effects that depend on the length, and this is a pretty nonlinear relationship between the length and the output current. Okay? And so what this says is that we really cannot use the length effectively in order to scale these currents. Okay, and so if I want these currents to match, my best strategy is to use L1 is equal to L2. Okay, and so this strips away one of our potential degrees of freedom. And so that leaves really only the width. We can change the width of these two devices in order to scale the current. And here, if we look at this from a layout perspective, let's say that I had transistor 1 and I wanted to make transistor 2, M2, twice as wide. Okay, so now these have the same length for both of the devices, but M1 is, call it a length of 3, and M2 is a length of 6. Um, this is a little bit problematic still in advanced technology nodes, in particular because modern transistors don't really look like the rectangular geometries that I was showing on the previous slide. And so simply doubling the length of the drawn device doesn't really double the current, okay? And it's really when you start to dig into why that's the case, it occurs because of what I'm going to call the edge effects. And so if I was to draw a transistor versus what it actually looks like, it's really the rounding of these edges and these corners that doubling the length doesn't necessarily reduce or result in twice as much of the, doubling the width doesn't result in twice the area of the transistor. And so what you really end up wanting to do is you want to use what are called unit devices. You want to use devices that look identical, i.e. like this, and instead of using one of them, we simply use multiple devices and we connect them in parallel. And so this is really the way that we should be scaling current mirrors, is that I take one unit device, M1, and if I wanted to scale that by a factor of 2, I take what's called this unit device, I connect the sources together, the drains together, and now this will result in a transistor that is truly twice the area of M1. Okay. In SPICE, this is often called the multiplicity or the M factor of the device. And so M equals 2 simply means that we're taking this and we're multiplying it by 2 with the exact same connections for all of the devices. So in 164, we are going to build current mirrors many, many times in this course, and we are going to use unit devices and using this M factor in order to size them. Okay? Unfortunately, what this is going to do is this restricts the scale factor, i.e. that K that I was talking about on the previous slide, to be a rational number, where P and Q have to be integers, and the scaling factor is P divided by Q. All right, so a further optimization that you'll often see when you actually do the layout of this is that if we're going to start to use multiple devices, we can merge them together. And merging them together has a few advantages. First and foremost, it results in a more compact layout. But more importantly, and the reason why it's frequently used, is that it reduces some of the capacitance that we'll see. So instead of having 2 drains, we'll merge the drains together, and this will allow us to have less junction capacitance on the drain node. Okay. Now note, you could also merge the source nodes, but merging the source doesn't usually result in much benefit because the source is connected to VSS in our example, and I'm not concerned about the parasitic at VSS. I'm concerned about the parasitic at the output, which is the drain in this case. And so this is a layout technique that's known as fingering. When we start to merge together the multiple devices, we'll talk a lot about this in later courses. All right, so let's come back to our structure and let's look at, potentially what some of the errors are. So in the first slide, I ignored channel length modulation in order to get the concept across, but let's revisit this and let's look at what happens when we do start to include channel length modulation. So with this structure, this node is going to be set. It's going to be VOV of M1 plus VT, whereas this drain node, it is free to move based on the circuits that are connected up here. As this voltage moves, we know that the transistor exhibits some dependence on its output voltage. This is channel length modulation. And so if I was to look at the IV curve, we called the slope of this R out, or 1 over GDS. And so if I calculate how much error I get in the currents, I take I out minus I in divided by I in, and I get delta I divided by I in, where delta I is equal to the difference in VDS between these two voltages times the slope of this IV curve. And this is going to give me lambda times VDS, approximately. Okay, and so just as a simple example, let's say that we had lambda is equal to 0.1 divided by volts times a 1 volt difference. This would give me a pretty substantial error of 10% in my output current. And typically this is a little bit larger than we would like. So how can we go about fixing this? There's really two solutions that are pretty obvious. One, we can use a device that has a small lambda. Typically this means large length, or large L. Since we know that lambda is a function of L, we can simply increase the length, and channel length modulation becomes less of an issue. The downside about doing this, of course, is that larger L means that I also need a larger W, which is going to result in more parasitics. Or second, I could minimize this delta VDS. And so we're going to explore this technique right now. All right, so one way of minimizing the change in this voltage here is to add another transistor. Okay, and so this transistor, we're going to add, this is called cascoding. Okay, and this cascode device, essentially what it does is it protects this node Vx. Okay, and this should be pretty obvious if you write out what the voltages are. And so in this particular example, Vx is going to be equal to Vcas minus VOV minus VT. Okay, and so importantly, when the output node Vout is moving around, it's not changing Vx. Okay, and so Vx in this case can stay relatively independent of the output voltage, thus protecting this transistor M2 from seeing these perturbations. Okay? If Vx is not moving, then we can set Vx to Vi by appropriately choosing this voltage Vcas. Okay? And I can set VDS, delta VDS is equal to 0 in that case. And then I will perfectly copy the voltage from I in to I out. Furthermore, this has the additional benefit that when I calculate the output impedance, that is when I look back into the structure at this node, I see a much larger output impedance that's essentially proportional to GM R out squared due to this cascode. Okay, so normally I would see R out of M2, whereas this transistor adds this GM R out factor to it, giving me a GM R out squared. And so now the question is, what do I have to pay in order to get this nice benefit? Obviously now the voltage that I need at Vout is higher. So I've increased the compliance voltage in order to keep this device in saturation. Okay? And so if you were to calculate the compliance voltage in just 1 second, I'll show you a structure that shows this. You'll see that it's higher than just VOV, which is what we would need to keep M2 in saturation. All right, so here's one way of generating this voltage Vcas. What I've done here is I've taken two diode connected devices, this one, and I am copying their gates over to this node in order to mirror the current from I in to I out. In this particular case, what you will see is that if I was to write out the voltages, so V1 is equal to VOV plus VT, and VCAS is equal to V1 plus VOV plus VT. And so this node, Vx, is equal to VCAS minus VOV minus VT. And so if I solve for, if I simplify this a little bit, I will get that this is equal to 2 VOV plus 2 VT, and I'm subtracting off a VOV minus VT, so this is equal to 1 VOV plus VT, whereas now you see that V1 and Vx, these two voltages are exactly the same, okay? And so what that says is that this error term, the delta VDS, is indeed equal to 0. The only issue, as I just mentioned, is that the output minimum voltage is relatively large. And it's pretty obvious to see from this example, because the minimum voltage that I need to keep this these transistors on the right side in saturation here, this is equal to VOV plus VT. And I need to go up one additional VOV in order to keep this device in saturation. And so what that means is that I need 2 VOV plus 1 VT in order to keep both of the devices on the right side in saturation. So I have a much higher compliance voltage. However, I have delta VDS is equal to 0, and I get a very high output impedance. And so this structure is a very good current mirror in a lot of ways. What we're going to look at now are other ways of generating VCAS that reduce the minimum output voltage. And so really what we want is we want a structure, I'll call this a magic battery, that sets the gate of this cascode node right here equal to the lowest potential that I could possibly need. Okay, and so the lowest potential would be if I had VOV to keep this transistor in saturation, and I had VOV to keep this transistor in saturation, and so VO min is equal to 2 VOV. And so the question is, how do I generate a magic battery or a voltage that is equal to 2 VOV, that sets up this entire structure such that we have the minimum output voltage is equal to 2 VOV. This is what's known as a high swing bias because of the lower compliance voltage that's required. And so we'll walk through a couple of different ways now of generating this magic battery voltage to satisfy this condition. All right, so the very simplest way of doing this is to take a structure that is 1/4 of the width of the device. And so if we write out why this works, I want VOV right here. And so this voltage, I want this to be equal to 2 VOV plus 1 VT. And so I'm trying to generate a voltage that's equal to 2 VOV plus VT. And so if you write out the expression for a MOSFET in saturation, you can see that what I'm trying to do here is I'm trying to increase and add this prefactor of 2, okay? And since I have the W over L term, if I was to solve for VOV with this expression, okay, I would get that VOV was equal to 2I divided by KNW over L. And so if I wanted to set this equal to 2 VOV, you can see that I can do that by making W over L 1/4 the size. And so I get this prefactor of 2 by setting this equal to 1/4. That gives me 2 VOV plus VT at this node. Okay. So this circuit certainly works. The only downside about this is that the transistors that we're biasing, namely this cascode device over here and this cascode device, they're sensitive to the backgate effect. So the body of these is tied to VSS, since we can't tie it to the source, given that this is an NMOS. Whereas the transistor that's generating this voltage, its body is tied to ground. Okay, and so there's a little bit of an error here in generating this voltage precisely due to what's called the backgate effect. All right, so how could we mitigate this backgate effect? One way is to, instead of using one transistor that's sized 1/4 W over L, we can actually stack a couple of devices, as you've seen on the homework, in order to generate voltages that are a little bit closer. It's still not perfect, but it's much, much better. And this is probably the most common way that you'll see this done. And so typically you'll stack, if you wanted to do a 1/4 device, all of these will be unit devices, and then we can combine this bottom device here and make it a 1/3 W over L. This is a nice structure in the sense that it mitigates some of the backgate effect and gets us a little bit closer towards generating this voltage. However, sometimes you will want to change this voltage a little bit. So in our previous example, we used K is equal to 3. And if you do kind of work out the algebra of what region of operation these particular devices are in, you can show that for different K, you can generate different voltages for this particular structure. And so for K equals 3, you end up exactly at 2 VOB plus VT. However, sometimes you want to increase that voltage, in particular, that you don't want the voltage to be right on the edge. So for example, if there was a little bit of error or process variation, you could cause the transistor on the previous slide, namely this transistor, to enter triode, in which case it's no longer a good current source and no longer going to faithfully mirror that current. And so oftentimes you'll build in a little bit of margin by using a ratio for K that's slightly larger than 3. So K is equal to 5, or even sometimes K is equal to 8 in order to bump up that voltage for a little bit. Okay. Importantly, and you'll get to work this out in the homework, so I don't want to spend too much time on it right now. It's really important to realize that these two transistors are not in the same region of operation. Okay. Their gates are tied to the same voltage, and the current is the same. Okay, and so those two conditions should tell us that they can't have the same VGS, which means that they both can't be in saturation. Okay? So one of these two devices is in triode, whereas the other device is often in saturation, but can be pushed to triode as well, depending on the voltage. Okay? And so again, we'll work out this and you'll get to prove this equation in the homework. All right, so what else can we do with the structure? Well, the previous example, we needed 2 branches in order to bias the current. Here, you can show that you can fold this and you can reduce the number of required bias branches to 1. You're simply taking this structure that we had previously had below and you're stacking it on top of each other such that this bias current I1 biases all of these devices. So the nice part here is that we reduce one of the current branches, i.e. we have lower power. unfortunately, it means that we need a very high compliance voltage on the input side, which often means a high supply voltage. And this is quite sensitive to the backgate effect, given that this transistor up here, this cascode, is at a very different potential than this one. And so this is a common circuit that's used in older technologies. It's not used traditionally in many new technologies today. All right. There are times when we don't necessarily want the same W over L. So in all of the previous examples, we had assumed that W over L was the same for the two devices. Why is it the case that you might not want them to be the same? Well, W over L on the bottom, you'll typically use to get you large output impedance, okay? There's good reasons and, reasons that you'll find out about in 264A and 264B that you do not want a lot of GM here. You don't want a lot of GM because that's going to generate noise. And so you really want low GM. Okay? And this is somewhat conflicting with what we want from the Cascode device. From the Cascode device, we want large GM R out. We want a large GM R naught product. And so typically what that means is that we will make L2 much smaller than L1. L2 can be minimum length, whereas L1 will typically be much larger, 10 L min. So 1 micron or even 2 micron length in order to get good output impedance. The problem is that previously we couldn't handle this because we assumed that W over L was the same for all of the transistors. And so now let's work through what this particular circuit does and how it's a little bit different given the different W over Ls. So on the right side, we're still going to take this current and we're mirroring down this voltage in order to generate VGS for this bottom device. But now, instead of just stacking the structures like we had previously, we need to make what's called a replica of this circuit. And so what we're doing here is we are using this device, and we're summing the currents at this node. Previously, you'll recall that this used to be a 1/3 device. Okay, really, this is just like we have two of these devices in parallel. Okay, and that's where we get this factor of 2/3, is that really it's two parallel devices that are giving us more width because we're dumping twice as much current into it. Okay, but what you'll see is that this allows us to generate here the right voltage that we would need in order to put VOV here. Okay? And we can't simply take this voltage because now it would be the wrong VOV. And so that's where this M2 device that we've folded in comes into play, because it lets us generate VOV2 plus VT that is then subtracted back off on this side to get us back to VOV1. Okay, so again, very quickly, this voltage here generates VOV1. This transistor generates or shifts this voltage up by VOV2 plus VT. It's shifted back down by this device. And then at the end of the day, we are left with VOV1 here, which is exactly what we need in order to keep this bottom right transistor in saturation. Okay. All right, so if we wanted to mathematically show this, we can actually derive out the voltage, and I'll show you now kind of qualitatively what we did on the previous slide and what I was explaining. The big hint here is to realize that different currents flow through the upper and the lower devices in this leftmost branch, okay? And this should be very obvious. Here, I have I1, and I also have I1 coming from this side. And so what that means is that this transistor down here, this sees two I1. Okay? And we need to resolve the VOV relationship and keep track of it for W1 over L1 and W2 over L2 because they are different VOVs. All right, so this VDS1 voltage, this voltage right here, okay, this we can use kind of the previous expression that we had solved for VB a couple of slides ago, and we know that VCAS is equal to this voltage, VDS, plus VOV2 plus VT. And V1 is going to be equal to VGS1. That is this structure over on the left, which is equal to VDS1 plus VT plus VOV1. We know that ID1 is going to be equal to I1 plus I2. That's these two currents coming together that I was showing you down here. And so we can set up this relationship with the size given the two currents where Kn times 2/3 W1 over L1 times V1 minus VT times VDS minus VDS squared divided by 2 is equal to 1/2 Kn W1 over L1 times V1 minus VDS1 squared plus 1/2 Kn W2 over L2 times VCAS minus VDS1 minus VT. This is simply KCL at this node, realizing that this device is in triode. Hence why we're using this expression. All right, and so we just solved this above equation for VDS, very much like we did 3 or 4 slides ago when we were solving for VBS. All right, so now we know how to mirror currents, and coming back or thinking about the structure that I showed you on the first slide where we generated a voltage, we then used a current generator in order to ratio and to kind of tune that current. What we'll often do then is we will take these currents and we will mirror them and move them around the chip, okay? What you'll often see is that this is done in current form rather than voltage form. Okay? So if you try to move gate voltages across the chip, you have to worry about IR drop and other issues such as contamination of the signal. So for example, let's say that I had a current source and I had a diode connected device, and this was a very long trace over to the amplifier that I wanted to mirror it to. I have to worry about any resistance here, as well as if I had, for example, a trace that coupled clock signals onto this, it would contaminate this signal due to the fact that it's voltage mode rather than current mode. Okay, and so typically what you'll find is that we will only generate gate voltages in local circuits, and we will distribute currents across the chip if we're going long distances. And so what does this look like? It looks something like this, where we'll have a current mirror, or we'll have a circuit that's generating IREF. We will then mirror this current around to generate P-type currents and N-type currents and shuttle them across the chip as appropriate. Oftentimes you'll see people say that this idea of distributing the current, it wastes power or it wastes current in these auxiliary branches. And so you could be tempted to want to use very large mirror ratios. And so when I talk about large, I mean, mirror ratios of 100. This is almost always a very, very, very bad idea for the following reasons. consider that we had this structure down in the bottom right, and if I wanted to find the impedance looking into this node, the impedance is 1 over GM, okay? Whereas the total gate capacitance on this node is CGS from M1 and K times CGS from M2, okay? And so what this means is that the time constant at this node is 1 plus K times CGS divided by GM, or 1 plus K divided by FT, where FT is, again, the transit frequency of this device. And so what this says is that if I have a disturbance at this node, i.e., if I had a clock signal that coupled on some charge, it would take a very long time for this to settle if K was a large number. And so most companies will have policies regarding this, and we'll do the same thing in 164 to kind of keep it realistic. We're going to prohibit ratios of K being greater than 20. The other reason that's practical to limit this is that if you think about the, back on the slide 3 or 4, when we were talking about unit devices, once we start to get a whole bunch of unit devices, it becomes harder and harder to match them and get them to all be that same unit device. We'll talk about the idea of what's called process, voltage, and temperature variation, as well as its impact on these current mirrors in a subsequent lecture. So just know that in our class, we're going to limit K to be 20. And so a reasonable question is, what if you wanted a factor of 100 in the currents? The best way to do that would be to take current mirrors like this, where we could have a 20 to 1 ratio, and then a 5 to 1 ratio. And in this way, I'm going to get the 20 times 5 or 100 current ratio. And so obviously, if I want larger and larger ratios, I have to mirror back up and down multiple times in order to get those larger ratios. All right, moving on to generating reference voltages, we're going to look at several voltage reference circuits in the next handful of slides. Starting off with very, very simple reference voltages and then moving to more complicated bias circuits, okay? And so what I'm showing here is a current mirror, as we've been discussing for the last 45 minutes. But instead of supplying a current source, I'm using this resistance, R, connected to the supply voltage, VDD, in order to generate the input current, IN. Okay? And so what I'd like to do is I'd like to calculate the output current. This is pretty straightforward. We can write that I out is equal to I in, just given the sizing of M1 and M2. And so this voltage right here is simply equal to VOV plus VT. And so the voltage dropped across the resistor is VDD minus this VOV plus VT divided by R. Okay. The problem or the issue with the circuit is that the current, IN, is essentially proportional to VDD. Okay? And so if VDD was to change by X%, the bias current will vary by that same amount. Okay? Why is this problematic? Think about it in the following way. Let's say that you're listening to music on your iPhone, okay, and your battery is running low. So as you were to keep decreasing VDD or the battery voltage, we would not expect, for example, the amplitude or the loudness of the music to go down, right? Whereas if we were to use something simple like this, that would indeed be the output, is that the bias current would be proportional to the battery voltage. Okay? And so really, when we're talking about bias circuits, a lot of work goes into, as you'll see in just a few slides, getting rid of this variation. We want to make circuits that are independent of the supply voltage. And so oftentimes what this means is that we need to reference to a voltage other than the supply, okay? And so one very simple example of that is what's called a VT reference. And so a VT reference, as you might guess, um, we're going to use the threshold voltage as our reference voltage in order to start generating these currents. Okay? And so conceptually, this circuit looks very similar to the one that was shown on the previous slide with a few distinct differences. And so if we were to try to write the output current I out, um, if we knew this voltage here, VGS1, the current that's in I out is simply going to be equal to VGS1 divided by this resistor R2. Okay? And so the question is, what is this VGS1 voltage? This is really, if I was to come back up here, it's VGS1 is really kind of VT plus VOV of this device. Okay? And if I make the device sufficiently large, that is, if this transistor T2 or M2 is very large, we can make VOV much less than VT. Recall that VT is typically 400 or 500 millivolts. If I have a lot of overdrive voltage, or excuse me, very little overdrive voltage, I'm essentially just limiting this to VT. And so what that does is that sets this equal to VT and makes the output current essentially just equal to VT divided by R2. All right, so the question is now, given that the previous circuit had a linear dependence on VDD, how much does this particular circuit change the output current when we have variation in VDD? In order to answer that, we're going to introduce a concept known as the sensitivity, where the sensitivity is defined as when we have a change in parameter y, how much of, or excuse me, when the sensitivity of a parameter y to a change in a parameter x can be found using this expression, okay, where we're essentially taking the derivative with respect to y divided by the derivative with respect to x. And if we simplify this, we simply get that it's equal to the x divided by y times the partial derivative of y with respect to x. Okay? And so in our particular example, we're looking for the sensitivity in I out with changes of VDD. Okay? And so I'm going to break this up into two kind of simpler transfer functions and multiply them together. That is, how much does the input current vary with VDD? And how much does the output current vary with respect to the input current? And so you can see that these two, when I multiply them together, I'm going to get I out divided by VDD exactly as I want. The nice part about this, though, is that it's very easy to calculate given that we've already done this first one. We know that the input current with respect to VDD is essentially 1. Okay? That is that if it varies by 10%, this current also varies by 10%. And so the next one is we have to calculate how much the output current varies with respect to the input current. And so we're going to use the definition up here, and we'll get that it's equal to IN divided by I out times the partial of IN with respect to, or partial of I out with respect to IN. And if we plug in kind of the expression for I out to IN in the previous relationship, what we'll find is that it's equal to 1/2 times VOV1 divided by VT plus VOV1. Again, plugging in kind of typical numbers of 150 millivolt overdrive voltage with a 500 millivolt VT, we see that instead of having what would be 100% variation, we're getting down to about 11.5% variation. So we've reduced this dependence by about 8x using this other biasing circuit. And if you kind of go back to that example, the reason that we had that high dependence was that first prefactor being 1. Okay, the second prefactor was that 11.5%, and so it reduced that prefactor of 1 by 1/8 essentially. And so the question is there a way to maybe better generate that input current that is not quite so dependent on VDD? Okay? And so the idea here is that if I took this output current and I were to mirror it back to the input, okay? And so using T4 and T5, what I'm essentially doing is taking the output current, mirroring it back to the input, okay? Rather than generating an input current that's dependent on VDD. And so now I have a supply independent current. Um, the issue with this, as we're going to see with many of the circuits that are coming up, is that there's a potential that there's no current in both branches. Okay? And so to kind of understand this, you can kind of go through the math and think about if T4 had no current, T1 would have no current, no voltage would be developed at this node, okay, because this T1 device is off, which means that there's no current in T2, which this T5 would not mirror any current back. And so this is a perfectly happy operating point. This circuit is what's called bistable. It has two operating points, one of which is all currents are equal to 0, and the other current, or the other operating point, is when I out is equal to VT divided by R, as we previously solved for. And so how do we get this circuit, quote unquote, started? How do we kick it towards this second bias point or operating point where it is functional? And so this is what's known as a startup circuit. The startup circuit essentially looks at various different nodes within the circuit and tries to kick us out of this undesirable operating point and put us up where we're operating with current on this device where we want to operate. Okay? The way that this works is actually pretty straightforward. If we look at these two devices, T8 and T7, these are essentially an inverter. Okay? The sizing of them is such that we're moving the trip point higher. Okay, and so instead of, a normal inverter would have the PMOS being 2.5 to 3.5 times larger than the NMOS. In this case, we're making the PMOS device weak, which means that we're making it smaller than the NMOS. That has the effect of pushing the trip point voltage higher. Okay? And this trip point voltage, it's watching this voltage here, B. Okay? And so when B is too low, okay, it turns on T9, and T9 starts to pull current out of this node. Okay? And when this node starts to get yanked down, node B is now going to come up. Okay? When node B comes up, it's going to turn off this inverter. Okay? And so an ideal startup circuit is exactly like this. It finds when the circuit is in the non-ideal state or the undesired operating point. It turns on, kicks it to the other operating point, but more importantly, once it's at that second operating point, it gets out of the way and it doesn't interfere with normal operation. Okay? And so there's a whole bunch of various different permutations on bias circuits or on startup circuits rather. This is a very classic and simple startup circuit. You could imagine you could do almost exactly the opposite of this. We could sense the voltage at node A, and we could pull around the voltage at node B in order to get it to operate. All right, so let's look at another reference circuit. Instead of a VT, this is what's known as a delta VGS reference. Okay, and so what we're going to do now is we're going to calculate this current IREF P. Okay, and so very quickly, what's going on here is that we have transistor M1 is diode connected. This transistor up here is diode connected as well, and so we're getting this kind of recycling of the current as we did in the previous example. Okay? And there's a startup circuit that's not shown here that does something with these two nodes A and B. Okay? And so if we think about what happens in this particular circuit, we're going to develop a VGS at node V, and then we're going to drop part of that over this resistance R2. Okay. Now notice that M1 and M2 aren't the same sizes. M2 is M times M1. Okay. And so if we want to solve this, what we really need to do is just write a KVL loop around here, okay, where I have IREF times R2 is going to be equal to VGS1 minus VGS2. Okay? And this is where it gets the name of a delta VGS, is because it's the difference or the delta between these two VGSs sized differently. Okay? And so if I factor out and solve for VOVs, then I can start to pull into this the sizing of the device, where I get this root M based on the VOV expression and how we size M2 relative to W1. And then I end up with this rather interesting result where IREF is equal to VOV1 times 1 minus square root of M divided by R2. Okay? And you might be asking yourself, this seems like a rather strange result. Why would we want this? How is this useful? And it turns out that it's actually a really useful circuit. If you think about what the transconductance of the device is, the transconductance of transistor 1 is equal to 2ID over VOV, or 2IREF divided by VOV1, which is equal to 2 times this 1 minus 1 divided by square root of M divided by R2. Importantly, in this expression, we see that the transconductance is independent of the supply voltage, it's independent of VT, it's basically independent of all of these parameters. It only depends on two things. It depends on M and it depends on R2. Okay? And so this circuit is more often called a constant GM reference. Okay? And so rather than the previous kind of references where we were making a constant voltage or a constant current, this one is making a constant transconductance. So any of these devices that I connect up to these two nodes, for example, this transistor here or this transistor here, they're going to have a constant transconductance. Okay? Now note, this means that the current is not going to be constant over temperature. It actually changes in order to have the transconductance be constant over temperature. Okay? And so you're going to do this on homework 4. You're actually going to design this circuit, and we're going to design for some specs, and we're going to simulate this over a fairly wide temperature range to show indeed that the transconductance is constant over temperature. A few things that help with this circuit. Very often this is used in products. It's used in academic chips all the time. You will typically use an off-chip resistance in order to set this GM precisely. If you recall back to lecture 1, in integrated circuits, it's very hard for me to set an absolute value for a passive device, i.e. a resistor or a capacitor. If I wanted to match two resistors, I can do that very well, but I can't make a 1K resistor accurately. Okay, and so oftentimes what this means is that I'm going to use an off-chip resistor in order to set this bias current. If I want to minimize some of the mismatch that we'll talk about a little bit later in this course, it typically helps to have a large overdrive voltage. So it's useful to think about that when you're sizing this, that you want to have VOV1 be relatively large. And you want to minimize the backgate effect of the second device M2 here. You'll notice that the backgate of M2 would be connected to ground, and so M2 is a little bit sensitive to the body effect. And we can mitigate that somewhat by making the voltage drop across that resistor R2 relatively small. Okay, and so I times R2 is usually minimized in order to fix that. And so what that means is that often R is a quite large resistor. All right, so let's look at a couple of other reference voltages. This one is known as the VBE reference. Okay, and so very similar to what we've been doing with the delta VGS reference on the previous slide. However, here we've added this transistor Q1. So we've added a BJT, and we want to now calculate the output current, I out, and this current here, I bias. So we're going to do the exact same kind of expression that we did before. We're going to do a KVL loop around this where we will get that we have VEB, VBE plus VOV plus VT. That's to get up to this node, minus VOV minus VT minus I times R is equal to 0. Okay, and these cancel out. And so we're left with this VBE divided by R is essentially our output current. Okay. You'll notice that most oftentimes in CMOS devices we don't get a good BJT, but we do have parasitic BJTs. We have bipolar junction transistors that we're able to create what are called lateral BJTs instead of vertical BJTs. And these are parasitic devices, as I'll show you in just one slide how we can make them. So if you think about how we make a MOSFET, if you have a PMOS, we have two diffusions that we use for the source and the drain. This is the gate, and we put this all in an N well because we have a P substrate. If, on the other hand, you were to look at kind of this vertical cross-section of the device right here, you can see that a vertical BJT, we would have the emitter, we have the base, we have the collector, which we can make this structure using a standard CMOS process. This doesn't require anything special. The one caveat to it is that the collector, this bottom terminal, has to be in the substrate. And since it's in the substrate, that means that it has to be tied to VSS. Okay, it has to be the lowest potential. We can also do this just using this kind of structure that's shown on the right side. It's exactly the same thing. The only difference is that here we're using kind of a different geometry in order to make the device. These typically have fairly large area in order to get the right area of the BJT for the substrate PNP. All right, so now I want to look at the temperature dependence of these circuits. So we've looked at the supply dependence, but a really good reference voltage or current should also be independent of temperature. Okay, and so one way of quantifying this is the fractional temperature coefficient. And so what I'm looking at here is how much does I out change as a function of temperature relative to the original I out. Okay? And so if I was to go back in and calculate this for that circuit that we just looked at, we said that I out was equal to VBE divided by R. Okay? And the partial derivative of I out with respect to temperature is 1 over R times VBE, the partial derivative of VBE with respect to temperature, minus VBE divided by R squared times the partial derivative of R with respect to T. So here, I'm just looking at how much does VBE change as a function of temperature and how much does R change as a function of temperature. Okay? And so if I put these together and I simplify this a little bit, I will get that the fractional temperature coefficient on the previous slide is equal to 1 over VBE times delta VBE divided by delta temperature. This, we know how much it changes, times or minus 1 over R divided by delta R over delta T. Okay, and so if you look at the temperature dependence of a BJT, VBE changes by -2 millivolt per degree C. Okay, and so for a nominal VBE of 600 millivolts, this gives us minus 0.3% change per degrees Kelvin. And then if we look at the temperature, there's different ways of implementing the resistor. If we were to implement the temperature with a poly resistor, poly has what's called a positive temperature coefficient. And so the temperature coefficient can be roughly plus 0.2 degrees per degree Kelvin. Okay, and so when I combine this all together to get the the fractional temperature coefficient, you can see that I have roughly half a degree or 0.5% per degree C. Okay, and this sounds pretty good until you actually think about the temperature range that you could expect. If I was to take a fairly large temperature swing, but 100 degrees Kelvin, you could end up with 53% difference in the current over that 100-degree temperature swing. Okay, and most circuits are designed to withstand 100 degrees, and the military spec is even more than that. Okay? And so we need to do something to the circuit in order to improve its temperature dependence a little bit. So let's look at another reference. This is called the delta VBE reference. Okay? Again, very, very similar to the previous slide. We're going to write KVL around this loop. And you'll notice that now we have a BJT on this right side, and the BJT is going to be n times larger than Q1. Okay. All right, so if I was to write this KVL, I would get that VBE1 plus VOV1 plus VT minus VOV1 minus VT minus I times R minus VBE2. And so that's where we get this expression right here, is that I out times R is equal to VBE1 minus VBE2, hence the name delta VBE reference. Okay. VBE, so if we recall back to the BJT expression, you have that IC is equal to IS, EXP of VBE divided by KT on Q, or VT. Okay. And so if I solve that, I get that VBE is equal to KT on Q times the natural log of IC divided by IS, where IS is the saturation current. Okay, and so I can rewrite this expression as follows, and then I can use the natural log rule in order to combine these. IS is going to be the same in both of these two, excuse me, undo that. IS is not the same. Eraser. IN is the same in both of these two devices. IS is essentially proportional to the area of the device. So putting N of these devices in Q2 in parallel will give me N times the saturation current. Okay. Hence, the ratio of IS2 divided by IS1 is equal to N. And so this current I out 2 is equal to 1 over R times KT on Q times the natural log of N, where N is the ratio between these two devices. Okay. All right, and so now if I calculate the fractional temperature coefficient of this, if I differentiate the output current with respect to temperature, it's equal to ln of N, which is independent of temperature, times R times delta VT over T minus VT times delta R over T, where VT is equal to KT on Q. Okay. If I simplify this, I get that it is equal to the natural log of N times VT divided by R times 1 over VT times delta VT with respect to T minus 1 over R times the derivative of R with respect to T. And so again, further simplifying this expression, I'm left with this expression. And if we plug in numbers for this, what we'll find is that the fractional temperature coefficient is equal to roughly 0.13% per degree Kelvin, okay? And this happens because these two temperature coefficients partially cancel out, okay? So they have signs that oppose each other. And so this brings up the idea of what's called a band gap reference. And the band gap reference generates two voltages and combines them in a clever way. Okay? So a VBE has a fractional temperature coefficient that is complementary to the absolute temperature. So this is what's called CTAT. Okay? A delta VBE has a fractional temperature coefficient that is proportional to the absolute temperature. So it's called PTAT. And the idea of a band gap reference is to combine a PTAT and a CTAT voltage to make a reference voltage that is independent of temperature. Okay? And so what I'm showing you down here on the bottom is an example where we can take a CTAT. So this is our CTAT. And we can take a PTAT. And we can apply some gain factor in order to get these two slopes to be correct. And if I add these two slopes with the proper gain factor, I will get a voltage that's known as the band gap voltage. The band gap voltage is dependent on the band gap of silicon, okay? And so it is independent of temperature, and this is the whole idea of what's called a band gap reference, is to generate a voltage independent of temperature, independent of VDD, that is roughly equal to 1.3 volts. Okay. All right, so how does this particular reference work? Here's a couple of examples of a band gap voltage. So on the left, this circuit is something that we just looked at. Okay, we have this device that's size n times larger than this. We have the resistance, and so we know that this circuit, this is going to generate this PTAT current. Okay, and so by copying this over with M3, we're essentially generating IPTAT. Okay, and then we're dropping this over R2 and this BJT. Okay, and so this BJT is going to give us a CTAT, and the ratio between R1 and R2 is going to let us scale this such that we can correct for that gain factor that I was talking about. And so IQ1 in this example is equal to IQ2 is equal to VT divided by ln of n divided by R. That's what we talked about earlier. And then we said that Vref, this voltage here, is going to be equal to VEB3 of Q3 times, this is the K factor K, times VT times ln of n, where n is again our ratio between Q1 and Q2. Okay, and so this is one way of generating a supply independent voltage. Notably, in order for this to happen, we need W over L1 equal to W over L2, and W over L3 equal to 4 and 5. Sorry about that. Sorry, this should be 4, this should be 5, this should be 1, 2, 3. So essentially 1, 2, and 3 all need to be the same. Not surprising, they're connected all to the same gate. And 4 and 5, these two devices that are mirroring here also need to be the same. Alternatively, we can implement this with an amplifier This amplifier is essentially taking the place of the diode connected device. It provides a little bit more loop gain, as we'll see later on in this class, that can be useful for this. Functionally, it's exactly the same in how it generates this output reference voltage. All right, with that, we've spent quite a bit of time talking about ways of, one, generating accurate voltages, including their temperature and supply independence, generating mirroring currents, and also generating currents. Thank you.